Hey everyone. Well, I really hope those questions really start to make you think about some of these processes that you may otherwise take for granted and what's actually going on. So in this video, we're going to talk about pressure in Coriolis and how they affect some of these surface currents that we're talking about. So to kick things off, I thought since I just got some new tires on my bike here and I need to break them in, I think I'll take the long way home and see if we can't talk about some of this stuff. So stay tuned and I'll see you on the road.
So first thing, I guess if I want to keep doing this, I need to start leaving work earlier. I'm going to run out of sunlight. Anyhow, so pressure. What is this pressure thing I'm so concerned about? Well, you guys may have an idea of pressure and what it means, and you may know exactly taking a physics class or something, but we're going to keep it fairly simple. I will ask you to do a little bit of math, but try and keep it as minimal as possible. Okay, so simply put, pressure is a force over an area. And for our purposes, for what I'm going to talk about now, and pretty much most of what we're going to do in oceanography, that force we're talking about is just weight. So let's say it's a weight for an area. So as an example, I said I'm breaking in some new tires here, some motorcycle tires, right? You guys have seen them. I have two tires, and they're not really that big. So what does this mean for me vice a car? So let's say, all right, so my motorcycle and me included, let's say we're about 800 pounds, all right? Whereas the car is around 3,000. Now all these numbers are going to vary depending on the type of car and type of bike, but that doesn't really matter for now. So for me, all right, so if you Google this, which I had to do, I was too lazy to get down and measure it myself, the area that a tire touches on the road for a motorcycle is about the size of a credit card. All right, and I kind of measured that, and that comes out to be about 6.5 inches square. So 6.5 square inches times two tires, and that's 13 inches square. All right, so 13 square inches is my area that I touch the ground. And what that means is that 800 pounds is my weight over the area. So 800 divided by 13 is, wait for it, about 61 and a half pounds per square inch. So for every square inch, about like that, 61 and a half pounds. Now, if you look at a car, it's 3,000 pounds, right? 3+ times as much as a motorcycle. But a car tire puts around 36 square inches on the ground, each tire, and there's 4 tires there. So that comes out to about 144 square inches. So if you take 3,000, right, weight over area, divide it out, you get about 20.4 pounds per square inch. So I have a lot more pressure on the road. So even though my bike weighs a lot less than a car, that 61 and a half pounds for every square inch is 3 times as much as a car that is only putting down 20. So pressure matters, okay? That makes a big deal. I have more friction and contact with the ground necessarily than a car. And again, depending on the car, depending on the tire, depending on the bike, these numbers can vary a bit. But you guys see how important this can be. So let me try and give you a somewhat oceanography example here. So let's say a human, all right? Sorry, I'm make a turn here. And I'm going to compare a human and a polar bear. So the next thing about weight is, we say pounds, but in science we use something called newtons. And this is important because I've already talked about this. We talk about mass. And weight really is a force. And I said that pressure is a force over area. So force is a mass, remember stuff, times some sort of acceleration. And again, for most everything we're going to do in oceanography, that acceleration is due to the gravitational pull of Earth. And that is always, always, always going to be 9.8 meters per second squared. And that means 9.8 meters per second, so a speed, it's going to increase every second that much. Don't worry about it too much what that means. Ask if you want. That's not important right now. But what is important is that number and those units. So let's take a human. And we're going to talk in kilograms now instead of pounds, because kilograms is mass. That's stuff. So on planet Earth, on Mars, on the moon, it doesn't matter. A human is about 70 kilograms. So on Earth, that mass, 70 kilograms, times that 9.8 meters per second squared, gives you 686 what we're going to call newtons, okay? Because again, if you came up with this and you get to name it, all right? So Newton came up with it, he gets to name it, and that is just a kilograms times meter per second squared is a newton. So 686 newtons. That's the force that a human puts on the Earth. Now, a polar bear weighs a lot more, right? About, or I should say weighs, a lot more mass, about 450 kilograms. So you multiply that times 9.8 meters per second squared, and you get 4,410 newtons. Okay, 6 times the weight, the force of a human on the Earth. Now, here's where pressure is really important, because pressure is that force divided over the area. So a human foot, okay, that's about 100 square centimeters. We got to convert it to meters, whatever, 2 feet, anyhow. What you end up with is taking that 686 newtons and dividing it by that area, and you end up with something like 34,300 pascals. And later in the video, I'll kind of explain what a pascal is. It's just our unit of pressure. Now you take that polar bear, and their foot, just one foot, is about 7 times the size of a human foot. And they have 4 of them. All right, so sort of like that motorcycle car analogy, but even more so. So if you do the math there, and you take their massive 4,410 newtons, and you divide it by that area, you end up with about 15,750 pascals. So what you'll see is, though, that even though a polar bear weighs about 6 times as much as a human, the pressure that they put on the ground is about half of that. And the reason I say this is somewhat relatable to oceanography is, I talked about earlier, a polar bear is in fact a marine mammal. And they're specifically and especially adapted to live where it snows. So what that means is, because even though they're so massive, they have all that area on the ground, they're able to walk on snow. So they're actually able to move across, sort of like if you guys have ever been snowshoeing, and, oh, sorry, I'm running into some traffic here. If you've ever been snowshoeing, you know that those big snowshoes actually help you walk across the snow. You don't sink, and that's what polar bears do. So this is why pressure is so important, because weight or force isn't the entire picture. That pressure is. So you take something massive, but you spread it out over a bigger area, and the pressure is not quite as much. So here's my last example before we move on, and I get home and have to make dinner. So if you've ever seen a bed of nails, you know, one of those party tricks is somebody lying on a bed of nails. Well, what I would tell you is, I would much rather lie on a couple thousand nails than one nail. So here you can see, if you take a water balloon and you drop it on a bed of nails, it doesn't necessarily pop. That's because that force of that water balloon, the weight coming down, being dropped, is spread out over more nails. So the more nails absorb a lot of that force. And you get, for each individual nail, there's very little pressure, so it's actually not enough to puncture the water balloon. Now the flip side, if you take one nail and you take it to a water balloon, well, catastrophe. And yes, I did say catastrophe. So with that, hope you guys understand pressure a little bit more. And we're going to take this information and we're going to use it to explain some of those questions I asked you. So stay tuned, and I'll see you back inside.
All right, guys, so last time we talked about these surface currents, the ocean gyres, right, moving this warm tropical heat northward, cold water southward, I guess in the northern hemisphere. We should say equatorial to poleward would be a little bit better. And we know that this is because of this uneven distribution of solar heating, right? The equator area, the tropics, get more direct sunlight than do the polar regions, right? That's more diffuse. And what we end up with is this difference in heat distribution. And we also said that these surface currents are wind-driven. And then at the end of that, you know, just when we thought we knew everything, I asked you guys 3 questions. And we're going to try and tackle a little bit about that now and then in the next couple of videos. So what I asked you was, number 1, why do these currents travel in a circle, right? We said that these ocean gyres move in a circle. I said, why does the wind blow across the planet? And then I also asked you, what is wind? What is air? So the first one I'm going to tackle today, and this is sort of the introduction on force and pressure, is we're going to talk about the wind. So we see here, just like at the equator where it's nice and warm, less dense air rises, and then it cools off where it gets a little cooler and falls. And we did say, it's not this massive movement of air. You get these cells, and that's because of the rotating Earth. So what we're interested in is this surface current of air. And it might seem intuitively obvious to you that, well, of course the wind moves side to side. Why wouldn't it? Well, that's also one thing I want to point out about science is one of the great things is there are things that we might take for granted and that humans took for granted for thousands of years before finally going, well, does that actually make any sense? So while you might think, well, of course this makes total sense, let me give you one other example. So here's our room again, right? So we have our radiator over here on one wall, and we have our open window or poorly insulated window on the other. And in one case, the air heats and rises. In the other case, it cools and falls. And we know that. We saw that. This is sort of like the tropics, and this is sort of like the polar regions. And then what we want to talk about, what we're interested in, is this current right here. This is our surface current. This is the current that drives those, this is the surface air current that drives our surface ocean currents. Well, while this may make total sense to you, let me ask you, why is it that when this hot air rises, it doesn't just pile up here? Or when the cold air falls, it doesn't just pile up here? Why does it move? All right, well, I'll say two things. Number one, it sort of does do that. And since we're talking about pressure, we're going to say that, okay, each one of these areas gives us a bit of high pressure. And while this, again, may seem obvious to you, let's go ahead and actually get into some of the calculations and figure out specifically, physically, why this happens. So let's try that, and then we'll come back. Well, before you guys fast forward through this section, when I say get into the mathematics, I'm going to show you a bunch of stuff, and I'll point out where I want you to take over, all right? But I do want to start out, like I said, this stuff probably seems obvious. Of course the wind moves in a certain direction. So I'm going to give you a couple examples that you'll probably know the answer to, and then we're going to see, specifically, physically, why this is happening. So my first example, let's just take a tub. All right, this is my really fancy tub here. And I'm going to put a barrier in it. So there's my barrier. And let's say I fill it with water, okay? And I fill it differently. So on this side, I have water to here, and this side of the tub, I have water filled up to there, all right? So then I'll say, well, what do you guys think is going to happen when I remove the barrier? And you're probably going to say, well, of course we know what's going to happen. All the water is going to level out, and you'd be right. So if I remove my barrier, okay, and I'm going to erase my water here. All right, what's going to happen is that water is going to level out to another level. Again, something that seems like you pretty much know that was going to happen. So let me give you another example. Let's say I have a closed chamber this time, all right? Like a cylinder of some sort, could be a gas tank, and there's a barrier inside that. And inside here, I now have, on one side I have gas, and it's, there's 5 molecules of gas. And on the other side, there's a lot more. All right? And again, I'll say, hey, what's going to happen when I remove the barrier? And you might be thinking, well, this is still pretty easy. All those little molecules are going to spread out, and it's going to look something like that. And you're totally right. But what is the mechanism for that? And that's what we're going to get into, and this is why pressure is so important. So if I go back to my barriers here, let's put barriers back in both of these. And, again, on one side I had water here. I don't remember which one was higher. And here, a few molecules and a lot of molecules. Well, the reason why these things will level out is because of pressure, okay? Now, we did say earlier, pressure is that force over area. We're just going to stick with pressure for now, and we'll come back to that. So on one side, we have a pressure 1, and pressure 2. Same here, pressure 1 and pressure 2. And in both cases, pressure 1 is less than pressure 2. And that has to do with the fact that there's more stuff, right? Remember, pressure is force over area, and force is mass times some sort of acceleration or gravity. So more mass is going to give you, in this case, more pressure. So what happens is that mass is going to move, and it's going to move this way. it's going to move in the direction of from high pressure to low pressure. So I have a feeling I wrote over my little statements here, so let me erase this one up here. So pressure determines the direction of mass flow. That's why pressure is so important. Because we're talking about mass flow, because we're talking about currents, pressure determines that direction. And mass will always flow from high pressure to low pressure. So that's what's going on the planet, all right? And we'll come back here in a minute and I'll show you specifically on some of those figures. But I want to go in just real quickly and talk about how this applies to oceanography, because we're going to use some of this pressure a lot as we discuss oceanography. So this is great. You know, this is our pressures. I'm going to kind of get rid of this stuff here. Ta-da. And let me go ahead and let's do this. Let's pick a column. So we know, we have already talked about that pressure is equal to a force over an area, okay? So this column is sort of imaginary. Let's picture a column. Let's say this is a column of air, okay? So here, down here is the ground. This is the ground. You know, there could be somebody standing down here. Hello. All right, and this is air. Since we're talking about air, this could be a column of air up through the atmosphere. Well, that weighs something. It has mass, okay? So it's going to have a force pushing down with the acceleration of gravity, right? It's going to have a force. And then this sort of area of our imaginary cylinder, right, is an area. So that gives us our force over area. Same thing could be said. We could take another column and we could say, you know, in this case, this is underwater. So there's our water surface. Same thing though, right? Here's the bottom. There is a force and there is an area. Okay, so in both cases, it's a force over an area. Well, here's where it gets kind of tricky. You know, unlike motorcycles and polar bears, we can't just put a scale underneath an imaginary column of water or an imaginary column of air and measure it. We can't weigh this stuff. And so in lies a problem. We can't weigh it. And also because this is imaginary, what area are we going to use, right? It's the ocean floor, it's the surface of the earth, so this becomes a little bit tricky. So I do want you guys to understand that pressure is force over area. And what I'm going to do now is I'm going to show you some algebraic and geometrical trickery to get us to a way we can actually calculate pressure in the atmosphere and underwater. And by the way, in the water is going to be really important, so this is where this is going to come into play. So I'm going to get rid of this here, and I'm going to sort of start over. But I'm going to give you guys a different figure. Let's keep that up. Let's get rid of these. And let's give us a big cylinder. So same sort of thing. This is a big cylinder. And it has, you know, down here, still has an area of some sort, right? Area of a circle. Don't worry about it too much. And this can be anything. This can be air or water. Let's just say it's water. And it has a force, all right? Force pushing down. And we know that, again, that pressure is force over area. But just like I said, we can't measure this. So what do we know? So let's start with pressure equal force over area. And we already said that, okay, well, we know that that is equal to mass times gravity over area. But here's the problem. So I'm going to change colors here. This mass and this area are what we don't know. We can't weigh it, and we don't know this imaginary area. So we got to figure this out. And the reason I'm using a cylinder, you'll see in a minute, because it's an imaginary cylinder. So the first thing is for a cylinder, the volume of a cylinder. So we're going to say the volume of a cylinder is equal to its height times the area in the bottom. And that height just means, you know, from here to here. And again, this is arbitrary. That is our height. It's there to there. Great, we have that. And then we also want to figure out something for mass. Well, what's another thing we know about mass? Well, we've already know about density, right? And density is really important in the ocean and in the atmosphere. And we know that density is equal to mass over volume. And just again, doing a little bit of algebra here, I can rearrange this so that I have mass. And that is the same thing as saying mass is equal to density times volume. Well, now I have two equations with volume in them. And And no, we don't know volume either, but this is going to give us the opportunity to get rid of that. And you'll see what I mean here in a minute. So let's go back and let's just start right from the beginning here and start plugging all this stuff in. So I have pressure is equal to force over area. And that is equal to mass times gravity over area. And because of this formula here, I can say that that is equal to, I can replace mass with density times volume times gravity over area, all right? And then I can replace area, right here. So if we rearrange this one, we know that area is equal to volume over height. So I can replace that, and I can say density times volume times gravity over volume over height. Again, I'm not going to make you guys do this. I just want to see where this is coming from. And now you can see what we can do is we can get rid of that volume. So that was another one we didn't know. So it cancels there, and it cancels there. And what we are left with is something wonderful, all right? So pressure is equal to, still have density, density. We have gravity, gravity. And we have this height. And that ends up just coming up to the top there again, just a little bit of algebra. So pressure is equal to density times gravity times height. And in most cases, when we're dealing with fluids, whether it's water or air, mostly water in oceanography, we're going to know the density. You guys have already seen the density doesn't change that much in the ocean. Gravity, we're on Earth. I guess if you go to some other planet and do this, you're going to need another gravity. And then height is the thing. I mean, instead of height, you could just say depth. So we're going to know what depth we're at, or vice versa, we can figure out what depth we're at. So we have all the things we need to figure out pressure. And this is something called hydrostatic pressure. Hydrostatic pressure, all right? So going forward, yes, you do need to know this formula, all right? Rho GH, P equals rho GH, density times gravity times height. One more thing I want to show you guys, because I talk about units a lot, and I'm going to ask you, yes, you're going to have to use the hydrostatic pressure equation, and I want you to have the correct units. So this is how I want you to do it. If you just do this every time, you'll be fine. But if something doesn't work out, you'll know if you're not getting the problem right. And this is why units are so useful. So let me show you what I mean. Okay, we have our equation, right, the hydrostatic pressure equation. Pressure equals density times gravity times height. And we know the units for these. We've already talked about this. So in the case of, let's just say in the case of density, this is a mass over volume. And in general, this is going to be something like kilograms per meters cubed. Okay? Gravity is an acceleration. And that is going to be something like meters per second squared. And then height, well, we know height is just a distance, and that's just meters, all right? So that's what we're going to use for this. And there's a reason we go through this, and specifically these units. And I'm not going to make you go from grams to kilograms or anything like this. I'm going to keep this pretty simple. But when you do a problem, you're going to need to track these to get the correct units. So what this means is if I'm just, let's say I have one of everything. I have 1 kilogram per meter cubed for density, right, times 1 meter per second squared for acceleration times 1 meter. All right, so the numbers, I don't know where that circle came from. That's weird. The numbers don't really matter, but this is for the units. So the numbers you do on your calculator, and then just make sure this goes all the way through. So then what you end up with is a kilogram, right, meter per meter cubed second squared, if you put all those together. And what I want to show you is, you know, if you just run through this, yes, the 2 meters on top would cancel with 2 of the ones on the bottom, but don't do that. Only cancel one of them. So let me switch my color here. So I'm going to cancel one of those with one of these, and that becomes a 2. All right, so I now have kilograms meters per meter squared second squared. Great. And that is equal to, now I'm going to break this apart. And I'm going to break it apart by, let's see, grab another color. And the reason I didn't cancel both of them is I want to grab this section here this kilogram meter per second squared, all right? So that's a kilogram meter per second squared all over a meter squared, okay? The reason I did this is, oh, by the way, this kilogram meter per second squared is our, let's find another one, is our mass and our acceleration. So that is a force, that is our Newton. So this already gives us now newtons per meter squared, which is force over area. And that is equal to something called a Pascal, all right? And if you figure this out and you're some dead person and you did all this and you get to name it after you, so this unit is called a Pascal and we label it as a PA. So what I'll ask you on a problem is, hey, you're gonna have to calculate a pressure and I want you to give it to me in pascals and I wanna see that you go through this. You can take this, rewind it. Again, if you just copy exactly what I'm doing and make sure you're crossing this stuff off, you do this enough times and you'll start to see what I'm talking about. You know, come to office hours, ask for help, send me emails, but I do want to see this, and this is how you go through it. Okay, the important parts, now that we know hydrostatic pressure, we know that mass will flow from high pressure to low pressure, and pressure is what drives mass flow. So let's go back to our example in the room there, and then keep going and explain why these currents move across the planet. Here we go. Okay, and now you guys have seen with a little bit of mathematics really what's going on here. So yeah, this hot air rises and forms a bit of a high pressure here. Cold air falls and forms a bit of a high pressure here because that mass is building up. And what we end up with are these two complementary low pressure areas. So then what happens is this mass moves from high pressure to low pressure, and this one moves from high pressure to low pressure. And I'm totally feel like an evening weatherman now. And that is because, again, mass moves from high pressure to low pressure. So when you look back on our planet, currents are mass flow, right? We already know that a current is mass flow, and mass will flow from high to low pressure. So here, when the air heats up in the tropics, gets less dense and rises, we create this little low pressure area. And then up here where the air cools off and sinks, right, we create this little high pressure area. And then because of that, that mass will want to flow from the high to the low pressure area. Great, we've answered question one. Why do air currents move across the planet? And this is why. So whenever you hear weathermen talking about highs and lows, you know, what's also happening when we get these really intense high and low pressures right next to each other, that wind's gonna move really fast, right? It's gonna wanna get from that extremely high pressure to that extremely low pressure. We'll come back and we'll talk a little bit more about this when we get into storms later on in the semester, but that's enough for now. So question one is answered. And as we move on, or question two, whichever one the air current was, so to then begin talking about why these gyres move in a circle, why they have these strange patterns, it might not seem that strange right now, but we'll see how this goes. We have to stick with the air currents because air currents do something also weird, all right? So we just said it moves from high pressure to low pressure, however, not in a straight line. So in the north, this air current will actually curve. It'll curve westward. And the same thing in the south. It'll come up and it'll curve westward. So we get these curves, not just straight from high to low pressure, but an arc in both cases. So this phenomenon, you know, just to add to these couple other things, is rather than traveling in a straight line, air is deflected westward, at least in this case. We'll show you. It can go eastward in other cells, but we'll stick to these sort of tropical cells for now. Well, why is that? Why is it curving? Why does our air curve on the planet? Okay, well, hopefully, again, you guys are like me and you know that we live on a rotating sphere, okay? And some interesting things happen with physics on a rotating sphere. Now, not that physics is any different, it's just that when you're sitting on that sphere, that's your frame of reference, things look strange. We get some bizarre phenomena that just appear that way from where we are. I'll get into this in a minute. So we'll take this rotating sphere, Earth, and let's take a top-down view. So same thing, we're looking at Earth, so you can see Greenland here. This is North Pole-ish up here. And when the Earth rotates in this direction from the top-down view, okay? Just like you see here, so I'll leave that arrow up. Now what I want you to do is I want you to imagine a couple circles around the Earth. So I'm going to put a couple up here. You'll see this one is up in the Arctic, and this one's still pretty far north, but you know, it cuts through Canada almost to the US. And then I want you to picture there's a couple people. So we're going to stick one person right here in Canada. They're both very happy, and the other one in northern Greenland. Maybe not as happy depending on the time of year. And you know, Earth rotates once per day, right? Both of these people will end up right back where they were in 24 hours. So rotates around, they move around, super happy, not really knowing anything is going on, and they're back where they started. Well, what you'll also notice is that this person here had to travel a lot further in the same amount of time than the person further north. So depending on where you are on the planet, you're moving at a different speed. So it might feel like you're standing still because, again, we're on the planet, but you're actually moving. In fact, right here in Rhode Island, right now we're moving at about 750 miles an hour, all right? And what that looks like is this. So up here in the North Pole, right, you can see a person standing there, and as the Earth rotates, if you were right on the North Pole, you would just kind of rotate around. You wouldn't really notice anything. You would just move. And then the further you get towards the equator, the faster you have to go to get all the way back around. And this is where things get very interesting. So here's a little example. I actually like this one. I dug it up from a conceptual idea that London had for entering their subway system without actually having to stop the subway car. So you'll notice, you know, this little guy here starts out on a non-moving platform, and each subsequent walkway gets a little bit faster. And I guess the idea is here, the last one we move in the same speed as the train, and you just walk on. So this is, you know, kind of similar. So down here in the south, where again it's 0, and then as you move further north, it goes faster and faster, and that's sort of what's going on here. So he starts at 0, gets up to the first platform, and then up. And what you'll notice is to get up to each next platform, he has to speed up a little bit because it's moving faster. So if you were able to just walk north from the South Pole on the Earth, this is sort of what would be going on. Obviously, we're a lot smaller, so it's a little harder to imagine. And then what you'll also notice, if you were on this fast one, right, it would look like he's actually going the other direction. So think about when you're driving in your car, riding in a car, and you pass a bicycle. The bicycle's going the same way as you, but it looks like it's going the other way, all right? Because of that frame of reference. You are now moving, and it doesn't feel that way. So imagine also if you didn't have the benefit of standing on the ground and being attached to these walkways. Well, now we get into air currents, right? They're in the atmosphere. They're moving across the planet. Effectively, the planet is rotating underneath them. So I've got a few examples here. We'll try and tease these out and see how it goes. So the first one, just want you to focus in on a couple things here. So what this is this is say it's a merry-go-round of some sort, and we have a ball here. And the idea is you see this green line, it's a straight line. So standing back, you're looking at a merry-go-round from a distance, and somebody rolls a ball from the center out to the edge. And what you're going to see is that ball follows that straight line. So as we watch it, it goes around, that ball rolls forward, and it goes in a straight line. Great. Nothing too amazing about that. But if you're actually standing on the merry-go-round, what happens then? What if you're standing right here expecting to catch that ball? Like you're waiting. Here it comes. Well, let's use this line. Say you're standing right here. Well, as it goes, that line moves. All right? So you're moving away. So all of a sudden, all of a sudden, you're stuck up here. And yeah, I'm totally not going to go back and redo this for that one little hiccup. Just enjoy the blooper. Anyhow, you're standing here, and what it looks like is the ball is traveling on this line. So you guys see this curved yellow line. This is the apparent path of the ball to someone standing on the merry-go-round. So you could even think of it, if you're back here trying to watch this, all right? So I'm gonna try and back up, and I'm gonna put my finger right here. So say you're standing here and you're watching this ball, and ideally you're just gonna see the ball travel across. But what it really looks like is if you are moving, all right, well, what it's gonna start to look like is it's gonna look like that ball's coming right at you, all right? It's moving right at you. So that's the difference. So you guys can pause and redo this one and look at everything and wrap your brain around it, but I've got just another example to show you about this, and let's use the Earth this time, all right? So in our case, we're going to start up here at the top, just like the center of that merry-go-round, Ferris wheel, whatever, and we're going to throw something across the Earth, okay? Or there's a projectile of some sort, or wind, as we're getting to. And the idea is, if you're standing back away from Earth, that projectile is going to follow this path. So I'm going to play this, and what I want you to see is the blue line is that if you're standing back, you just see this thing go off the side of the Earth and go straight down, all right? And that was that original green line that we saw in the previous example. So standing back away from Earth, your reference is static compared to the spinning Earth. That's what it looks like. Well, if you're on Earth, just like you were on the Ferris wheel, well, now your path is that red line. All right, so I'm going to kind of zoom up here. So imagine actually you were standing on Greenland. So if we go back here, we can see that originally Greenland was right here. And while from an outside observer, it looks like that ball moves straight down. Well, from Greenland, it's going to look like the ball comes and curves or projectile or whatever it is. So keep your eye on Greenland and keep your eye on the red line. All right, so we're going to move forward. And the red line is what it looks like it did. Does that help? Let's hope so. So again, you're now standing here, and what you saw was this projectile curved, right? You're watching it curve around you. And that is all because we're standing on this rotating frame of reference, right? And that is something called the Coriolis Effect, all right? That is an observed deflection of a moving object based on being inside this moving frame of reference, in our case, a sphere rotating. So what you would see, say this is the opposite way, if you were at the equator and had a massive cannon and you wanted to shoot it towards the North Pole, well, if you're standing on Earth, it's going to look like it curves to the right. Because now it's moving from a really fast-moving platform underneath it, and this is moving much slower. So again, if you were hovering over these platforms, well, you're moving a lot faster, so it's going to feel like you're skipping ahead. Same thing in the south. If you move to the south, you want it to go straight, it's actually going to curve to the left. So importantly, this observed apparent deflection is Coriolis effect. Things appear to curve to the right in the northern hemisphere and the left in the southern hemisphere. You got to remember that. Right in the northern hemisphere, left in the southern hemisphere. So we put all of this together, okay, and we come back to our diagram, and we have our cells, okay? We already talked about that. High pressure, low pressure makes these air currents. We now know that that's where surface currents come from. And because of the Coriolis effect, we can see that these surface currents curve. So again, they curve to the left in the southern hemisphere, whether they're going north or south, all right, to the left. And in the northern hemisphere, they curve to the right that way, the right that way. And this is what you end up with, okay? So now we understand pressure. We understand the Coriolis effect. Incidentally, because of the, and you can kind of draw this out if you want to or ask questions, but just also know, because we'll come back to this, that that effect, that Coriolis effect, is stronger up here in the north and south than it is at the equator. All right, so that apparent force gets stronger and stronger the closer you head towards the poles. And that just has to do with the fact that those little changes as the Earth curves, you know, you move a little bit, that changes quite a bit. Those moving platforms start to get, the speed difference is a lot faster. Anyhow, so we're going to use this to move on to our next question, which is why those surface currents travel in a circle. All right, so why do we get here these gyres, these 5 oceanic gyres, do they actually travel in a circle? All right, so surface currents, right? Wind-driven movements of water at or near the surface of the ocean, we know that. So the force behind them is wind. So I want to make sure there's this distinction. You guys know the force behind surface currents in the ocean is wind. They are shaped by Coriolis and pressure. And that's what we're going to talk about next when we get into specifically how gyres work, is the shape of them is because of Coriolis and pressure. So you may hear the term Coriolis force thrown out there. I don't want you to use that. It is not a true force. It is an apparent force. So this is the way I want you to think of it. In case, for some reason, you may get asked this on an exam, surface currents are driven by wind and shaped by Coriolis and pressure. So think on that. Stay tuned next time, and we will answer not only why they travel in a circle, but why they have those peculiar characteristics that we saw last time, where these western boundary currents are those narrow, fast, deep currents, and the eastern boundary currents are a bit more diffuse. And then after that, we'll actually tackle this what is air thing, all right, before we move on to climate. So go ahead, take a look at your next homeworks, do the readings, come to office hours, and email me if you have questions, and I'll see you guys next time.